Brown University, and Cornell University, um, respectively. So now let's welcome Dr. Bill Chen. His topic will be heterogeneous integration. Thank you.
Bill, could you unmute yourself and
I am mute now.
yeah, and
Okay,
please
can you
share.
hear me now?
Yes, could you just share your slides?
I am sharing the slide, but if I'm not, let me try that again.
Yeah, we can see it. We can see it.
Okay,
You can
great.
see it? Okay. Okay, so today I'm going to speak on heterogeneous integration roadmap, a roadmap for a system of the future. COVID-19 is changing the world. Let me see how I can move my slide. Yep. COVID-19 is changing our world. As we continue through this pandemic, we are seeing enormous infection rates and immense tragedy, including loss of life and livelihood. This pandemic, we salute the incredible heroism, sacrifice, and resilience being demonstrated every single day. Over the past years, many of us have learned how to work from home, virtual platforms, through electronic products and electronic systems, just like what we are doing today. Very important with the accelerated advancement of virus science, resulting in rapid vaccine rollout. Testament to the spirit of global collaboration and shared goals. With the vaccine increasing across the world, we hope for a brighter future, a new normal. We are at the beginning of the end of Moore's Law, and it's important for all of us to work together to continue the pace of progress of electronics as we have over the past 56 years. We're entering a period of technology chaos driven by unprecedented level of discovery and innovation. CMOS scaling is no longer driving the pace of progress. The IT race is over, and the world is evolving in ways that we have never imagined before. This is a slide of the world's 10 largest public companies by market capitalization. The Economist magazine, one of the foremost business magazines in 2016, had an article about comparison between 2006 and 2016. And they show that in 2006, the first tech companies, Microsoft, is one of the 10 of the top 10. In 2016, the article in Economist show that there is 4 companies that are what we call 10 largest public companies: Apple, Alphabet, Microsoft, Amazon. But look at 2020. We have 8 companies that what we would call tech companies. Within that 8 companies, one of the company is Tesla. Tesla, people talk about, is just a computer on wheels. And then look at another company there, TSMC. TSMC is a company that provides semiconductors that make all the other 8 companies that are tech companies to be able to communicate, to be able to build their business around them. Semiconductor, therefore, is extremely important for us. Why this is so? Because there is a digital transformation of this global economy, and data is the new oil. So this slide, what we show is a slide from John Hennessy. John Hennessy is the chairman of Alphabet. And in this slide, he presented at the DARPA ERR conference on July 23rd, 2018. In this slide, what he showed is that between 1986 to 2003, the progress in processor performance is increasing at 52% a year, 52% a year. Between 2006 and 2015, the increase is at 23 and then 12%. And then after 2015, it is almost flat. That is to say that the process in processor performance has slowed significantly to almost flat. The next slide is come from a presentation by AMD CEO Lisa Su. She gave the talk at the DARPA ERR conference on July 15, 2019. And in that slide, she showed that the cost, she showed that Moore's law economics is meeting severe headwind. What she's shown is that costs continue to increase in terms of cost per yielded die for the 250 millimeter square. So increasing die size, therefore, is economically problematic. Moore's law economics is really having difficulties moving forward. The third slide I want to show is from John Schauf. John is from the Lawrence Berkeley National Lab, and he gave a talk called Computing Beyond Moore's Law at the International Supercomputer Conference on June 18, 2019. What she is showing is what the two people have shown previously, that they show that although the transistor count continued to increase, the performance as measured by thread performance, clock frequency, power, and core are all flattening out. And she asked the question, as that go in 2021, and then what? So obviously what we are looking at is how do we find a way out? How do we find a way to go forward? So let's go back to 1991, the technology roadmap, what we call ITRS. In 1991, the world's first open source technology roadmap, the National Technology Roadmap for Semiconductors, NTRS, was sponsored by the United States, US Semiconductor Industry Association. But by 1998, NTRS expanded. Europe, Japan, Korea, Taiwan joined US Semiconductor Association. So the roadmap then is formed, sponsored by 5 countries Semiconductor Association. It is called the International Technology Roadmap for Semiconductors. In 2014, the benefit of Moore's law scaling diminished, and decision was made by SIA together with the other partners to end ITRS. The last edition of ITRS was published on July the 8th, 2016. In March 2015, the ITRS's Heterogeneous Integration Focus Team signed an MOU with the IEEE CPMT Society to initiate the formation of the Heterogeneous Integration Roadmap. And this roadmap was formed with initiative from 3 IEEE societies: Electronics Packaging Society, Electronic Devices Society, Photonics Society, together with SEMI and ASME, Electronics and Photonics Packaging Division. The purpose is to maintain the pace of progress needed for electronic systems today and tomorrow by integration of separated manufactured component into a high-level assembly that provides enhanced functionality and improved operational characteristics. It is dedicated to embrace innovation wherever it arises and promote collaboration wherever possible to accelerate progress in this microelectronics landscape. Now, how is heterogeneous integration defined? As you can see in this picture here, is that you have die from one fab, die from another fab, maybe a different node, maybe some passives, some MEMS, etc., all put together into a single SiP. So it is heterogeneous integration by materials, component types, circuit types, nodes, and bonding and interconnection method, and very importantly, from different sources. So, so here we show an SiP module that has different enabling technologies, which we will discuss later: shielding, TSV, interconnections, antenna, all the other things that come together for our semiconductor packages. Our, our business is driven by markets. So market applications in this digital transformation is very important. So we identified 6 markets that are the leading important markets. So we call it IoT to IoE, smart mobile everywhere, data to the cloud, and data centers, autonomous vehicles, wearable, and health. We are not going to have any applications that is left behind. Now I want to bring back to look at the different technical working groups. And so we have the market applications, which is high performance computing, mobile, medical and health and wearables, automotive, IoT, and aerospace defense, the 6 ones we talked about. Then with heterogeneous integration components, we have part of the building block for our systems, single chip, multi-chip, photonics, power, MEMS and sensors, RF and mixed signals, cross-cutting topics, materials, emerging devices, test, supply chain, security, and thermal management, and integration process, SiP, 2D plus 3D plus 2D, and co-design and simulation. These are the basic building block for us for the roadmap, and each of those have a technical working group responsible for the chapter in the roadmap. The roadmap committee, I'm the chair, and Dr. Bill Bottoms, chairman of CMTS, is co-chair representing EPS, Professor Sebo Iyer, representing EDS, Professor Ahmed Helmi, chair professor at University of Toronto, representing photonics, and SEMI is represented by Tom Salmon, and ASME EPPD is represented by Ravi Mahajan, Intel Fellow, and ASME EPPD alternative, we have Gamel Rafael Ahmed, distinguished engineer at Xilinx. We have a global advisory council, Ajay Manocha, president and CEO of SEMI. Previously, he was chairman and the CEO of Global Foundries. And then we had Nicky Liu, founder and chairman of Itro Technology in Taiwan. Babak Sabi, Intel Corporation vice president, general manager for assembly, test, technology development, and Professor Herbert Lechner, the board of directors chairman for Fraunhofer Microelectronics Group and founding director of Fraunhofer Institute of Photonics in Dresden, Germany. So we have a global advisory council in Europe, Asia, and US. Now, the first edition of that roadmap was released in October 10th, 2019. Let me read off to you the a part of the press release. It's a heterogeneous integration roadmap. It's a roadmap for the future of electronics, identifying technology requirements and potential solutions. The primary objective is to stimulate pre-competitive research and collaboration across industry, academia, and government to accelerate progress. The roadmap offers professional industry, academia, and research in a comprehensive strategic forecast and technology over the next 15 years. The roadmap is available for download, and you can come to the Electronic Packaging Society website or the SEMI website, and they are available for download for free. As of today, I should say as of December 31st, last year, there has been download for 30,000 downloads as today. And we welcome you to download the roadmap for free. The roadmap, we have conferences and workshops and webinars. As you could see, we have conferences in East Coast of US, in Asia, and in Europe, and and many different conferences over the years. We also provide webinars, and um, we have webinars that covers the different chapters, and these webinars are also available for download, and also these webinars are free. Now, I would like to show you on the bottom left of the slide, we have a fourth annual meeting and workshop coming up on February 24th and 26th, and the registration is available at the Electronic Packaging Society chapter in Santa Clara, and there you can also register to come to our annual meeting and workshop for free. So I want to show some innovations and heterogeneous integration through system and package. Everything is changing. Maintaining the pace of progress will require new materials, new device types, new systems, architectures, and innovation, design cost, and time to market and security. You can see that what we are showing in our roadmap in terms of integrated photonics, AI and co-design, photonics, sensors, chiplets, plasmonics, all the important innovations that is crucial for us going forward. Here's an example of heterogeneous integration. On the left is a slide. On the left is a slide from the AMD's EPIC processor. This is a large die split into 4 chiplets at 14 nanometers tightly coupled. The next generation are 4 groups of 2 chiplets on each side of the larger IO die at 14 nanometers, while the smaller 8 dies on each side, these are 7 nanometers. So that shows a first generation, a second generation of AMD's EPIC processor. And this is part of Lisa Su's presentation on July 15th, 2019. Another example is Intel's embedded multi-die interconnect bridge. This is a product that Intel has been shipping. That's the Intel's Agilex FPGA chiplet application. You could see that the connection is made by the embedded silicon bridge called EMIB. The previous slide from AMD and this slide from Intel are both heterogeneous integration in production. Smartphones leads in the system and package implementation. So on top, on the 3 examples here is the Apple's A12 processor on a package on package. This is a wafer level packaging, POP, and in the middle, Samsung, and in the bottom Huawei. These are both advanced POP packages used in the smartphone, and they are also well known as being in production today. So this is the next is the DARPA's CHIPS program. And so DARPA has a program that want to put together custom chiplets and commercial chiplets so that there would be a rapid integration of functional blocks at the chiplet level. So this is presented by Andrea Olafsson at the Semiconductor West July 10th of last year in his talk, Extending Moore's Law Through Heterogeneous Integration. So what we have here is the Samsung's Galaxy 10. What you see is the teardown of the module, and you see the 5G modules. And for each of the phone, you could see that there is 3 millimeter wave antennas, and on the edge and also on other side, because you need to be able to have a good reception without having to have your hand or maybe some other materials that would be blocking the antenna. So this is a fan-out multi-stack integration that is from TSMC at the ECTC, showing at the ECTC conference 2019. That is a fan-out multi-stack integration. Another very good example of memory and SoC integrated together. This is a fan-out chip on substrate for the multi-chip integration. This is the hybrid module of 16 nanometers, 28 nanometers, using high density RDL to link them together. These are RDL 3 layers at line of space 2.2. Another example, 2.5D with silicon interposers, integrating high bandwidth memory together with processor. And this would be comparing how do we have from the traditional flip chip to the TSV. You could see that in this case, on the silicon interposers, the line of space is 0.5 and 0.5. Emerging medical devices technology. At this time of the pandemic, we are very much aware of how semiconductors might be important for us on the wearable devices technology. And one of our technical working group, one of our chapters is medical health and wearables. It showed different ways that the electronic packaging capabilities are being implemented in the medical devices that would help us in health and help to keep us safe. Silicon photonics, a co-package integration. This is the slide from John Schauf in his presentation. And what he showed is a schematic of how he sees the future of co-package could work in terms of integration. So this is a silicon photonics integration concept. And I think it is the same type of ideas that are going to be implemented into the future. This is in chapter 9 of our roadmap, Integrated Photonics. at the presentation on the 2019 Semicon West, the Cliff Young at Google presented 3 generations of the Google's tensor processor unit. You can see from left to middle and the right. What he showed is that the key element for maintaining progress is to use increasing power of available ICs, heterogeneous integration with available ICs, and innovations off the main path, and truly use co-design. And he felt that deep learning has invigorated the hardware. Now, what do we envision to be the future? At the SIA SRC report on March 30th, 2017, he said that the path forward is not as clear as was during the Moore's Law era. However, the enormous potential for economic and societal benefit, some that are envisioned and some that are not yet imagined. How do we reap the benefit of what SIA and SRC talk about, the economic and societal benefit? Alan Key, computer scientist, what he said was the best way to predict the future is to prevent it, is to invent it. And Philip Wang at the ERR Summit plenary last year, what he said is the future is system integration. Heterogeneous integration plays right into what all these 3 people have said. The heterogeneous integration roadmap is maintain the pace of progress needed for a complex electronic system today and tomorrow by heterogeneous integration through SIP. The goal is to promote innovation and collaboration to accelerate the progress in the microelectronics landscape. We are today at the convergence of technology chaos, business disruption, compounded by the COVID-19 global pandemic crisis. There's immense need for a pre-competitive technology roadmap for future vision, difficult challenges, and potential solutions. Heterogeneous integration through SIP is a powerful technology direction for system integration to accelerate progress for the advancement of technology to benefit humanity. The roadmap is for everyone, for you and me together. I'd like to quote from a speech from President John Kennedy. He said that we choose to go to the moon in this decade. I'm sorry, let's just get back. Professor John Kennedy on September 12, 1962 at Rice University. He was talking about the moonshot in 1962. He said, we choose to go to the moon in this decade and do other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one they are willing to accept, one we are unwilling to postpone, and one which we intend to win, and that others too. I think in that spirit is the spirit of heterogeneous integration roadmap. It is a collaboration of many people, many volunteers working together, many volunteers in the technical working group, and we work together so that we could do it for the benefit of our profession, benefit of our industry, and benefit for society. So thank you very much for listening. Stay safe and stay healthy. Thank you.
Thank you, Bill. Thank you for the wonderful speech. And we have collected some questions from our audiences. So here is, yeah, because we have a 5 minute Q&A session for Bill. So the first question we have is, what are the major technical challenges for heterogeneous integration?
Well, we have actually quite a different challenges on either on the personal level or on the um, people level. The most important challenge would be on how do we make the heterogeneous integration roadmap truly valuable for our community, for our profession, for today and the future. We see that also is a criminalization tool, educational tool, so that we have a very complex ecosystem in our industry, in our supply chain. So the roadmap is important for us to bring the supply chain together on this common goal. The second is that how do we increase the depth of our working group working together so that we can have a best overlap between chapters for the reader to read. And personally, I see AI and data analytics is here and now. And many of us, myself included, need to educate ourselves because we believe AI and machine learning will be important for our roadmap. So three different areas that we think are major challenges for us.
Thank you. Thank you, Bill. Uh, you talked about a lot in your talk, in your speech on chiplets, right? So the chiplet integration is the technology trend in packaging in semiconductor. So from your point of view, um, for Intel, AMD, Xilinx, their technology, what do you say about their advantages and shortcomings? Actually, for myself, I worked as a member of the R&D team, actually in Intel's Agilix chipset. I was one of them. So I like to know what do you think about the advantages and pros and cons of the Intel, AMD, and Xilinx chiplet products.
Ah, that you put me right at the spot. Yes, I think we had in the 2019, no, last year where we had our where we have our meeting, we I mean annual meeting, we have Intel to come and talk about chiplets, and we also have Babak Sabi from ODSA to talk about chiplets. And in February this year, we have AMD to come on the chiplets. My own belief is that in Intel, in AMD today, the chiplets that each of you are working on the applications that you have, on the interconnection method that you have. And how do you do this, for example, in terms of other applications that are difficult to say? I think chiplets is at a very early stage. And how do you implement it on laminate? How do you implement it on different platforms? They are all very specifically optimized for these different applications. So coming to our chiplet discussion on February 25th at 11 o'clock, and we will have a Zoom platform and we'll discuss it together.
Okay. Thank you. So my question, there's another question about the wafer fan out, because for the SIP, there is a fan out limitation today. And so what are the improvement status? I'm not sure if this is directly, related to your topic.
Oh, it is related because we have a
Cool.
chapter.
Oh,
We have a chapter called wafer level packaging, and we have a chapter wafer level packaging, which also includes the panel level packaging. And also we have that chapter include fan in as well as fan out. So your question of what are the limitations or the equipment limitations, is that what you're trying to say?
yes, yes. The fan out limitations, and what is the improvement status?
Oh, I think that the limitations is because we are using equipment that is used not exactly how shall I say it? Not exactly designed for this specific wafer level fan out. It is really fab equipment used for the fabs. I think the materials are fab materials being used. I think the equipment, um, how should I say it? The equipment companies and materials companies will continue to develop equipment specifically for fan out. I think the idea of people that has say that they want to use panel level, the idea that people were talking about they want to develop fan out in different directions. Think about this fan out. When did we start to talk about fan outs? It's only about 4 years ago, 5 years ago. And so I think we as an industry need to think about a long term where the materials and the equipment all come together in, in doing the job that it would do. I think I could see equipment people already are being coming together, and particularly, well, I do not want to name names at the point, but I would say that one very important purpose of the roadmap is to be able to say that this is the direction we are going. How do we develop the materials? How do we develop the equipment? And how do we make it so that it's most cost effective? And that design have to come in, reliability have to come in, quality have to come in. That is why we have 22 technical working groups, because they all need to be able to communicate with each other in the way that our industry communicate with each other.
Okay, thank you.
I have great hope, optimistic that we are going there.
Great, thank you. Yeah, so that's, I guess that's what the person who is asking this question is looking for. So the last question for the Q&A here is, besides the IC integration, what is the new demands for passive components in heterogeneous integrations?
You are speaking about something that I feel passives is a long neglected areas for research.
Mm-hmm.
And I, for one, have been very much is pushing the right word to say. So we in the we have an emerging materials group. An emerging materials group just describe the need for passives. We have a number of people in our power integration group, which describe the need for passives and have a roadmap for passives. And I'm always there to say that, hey, not ambitious enough. We need to describe the areas that is important for us in terms of research, because the research in passives has not been as ambitious, as dedicated as the research in the devices. Am I answering your question?
Yeah, I think so. Yeah,
Are you-
so
Go ahead.
yeah, so we have another panel session after the speakers, after the speeches. So I will end the Q&A here, and let's go to the next speaker. And after that, we'll have more time for a panel speech where we can also have some questions. Thank you, Bill,
Okay.
for your talk, and thank you for answering the questions. So next, we will go to Mr. Yao Jian Ling, who is the VP of R&D at the GCET Group. So
Hi,
here,
everyone.
hello, yeah, hello, Yao Jian. Let me get the slide of JCET to share to describe your company first. So JCET is founded in 1972, and it's the third largest OSAT company in the world. It's the which is the outsource semiconductor assemble and technology uh, and testing company in the world. It has more than 3,000 patents, and it has a comprehensive product portfolio in SIP solutions, advanced wafer level packaging, flip chip and wire bond, and discrete packages. Please go to Yao Jian's slide introduction slide. Therefore, I can describe him. Yeah, I can introduce him to the audiences. Okay, I think we got the wrong one. Yeah. Oh, here. Okay. So Mr. Yao Jianling, he's the VP and General Manager of R&D Center of JSET Group. He heads the China R&D Center for the JSET Group, and he focuses on the core customer technical support. He leads the advanced assembly technology and product development. And he has many different degrees from different schools, the Shanghai Jiao Tong University and University of Rochester, his two masters. He has more than 100 US patents in the field of advanced packaging. So let's welcome Mr. Yao Jianling to give us a speech. But first, for everyone, please ask your questions in the chat box so we can collect and ask him in his Q&A session, which will be 5 minutes after his talk. Thank you. So let's give the podium to Mr. Yao Jianling.
Okay, can you see my screen?
Yes, yeah,
Okay.
we're able to see.
Okay. Hello, everyone. Nice to meet you online. Today I will present the packaging fundamentals of high performance applications. As also William previously present, for the silicon node, the cost trend actually is keep increasing with silicon nodes progress in IC scaling is becoming more expensive, and also the associated yield can be problematic and be further affecting effective cost. From the slide, you can see from the left, the wafer product cost entirely covering manufacturing cost, engineering cost, and new product introduction cost. So the wafer cost is keep increasing with the silicon node scaling. And also the engineering design, because the mask layers cost increase is also increased. And also the new product introduction cost is increased for every technology node, because all these associated costs for the mask design cycle, all this and learning curve, including the yield ramp costs. And also here the right side from the MD HIR, it also summarized the entire effective cost after silicon node 14 and 16. The entire cost, the ramp rate is obviously increased. This page is summarized from the John Sharp HIR. Also, the performance trend is not matched. Actually, the silicon no progress does not seem to provide proportional performance and power benefits anymore. From here, especially the cross frequency, you can see from a long time, about 5 years ago is about 10 years ago is almost already saturated, and the power also saturated soon, and the thread performance also is flatly. So overall, this silicon node did not provide enough effective performance. Then here we can see the for different silicon technology intense product of CMOS logic, memory, and analog. From scale point of view, the CMOS logic is the best one. It can scale fast, and memory somehow is a bit late. And the analog actually is really not so catch up, and you will not be able to catch up actually due to its performance request and design request. And from technology, in no case, CMOS logic is the leading one, and memory is the second one, and analog is the third one. So interconnect layer case, CMOS logic has the most layer, backend layer, and memory has less, and analog somehow between. So from product development point of view, we have typically different approach. One is a transistor focus, is basically try to make the transistor density as high as possible. So you basically consider more on transistor scaling, and then better performance per cost. So and another view from the strategic point is to focus on system level, which focus more on increased functionality and lower cost. And technology case is more focused on technology, device and circuit innovation and system integration from the big picture level. For the system focus could actually can be carried out on either this chip level or package level. The chip level case is SoC, which means system on chip, and system package level is SiP, system in package. For example, the SOIC, but the latest progress is TSMC's SOIC, is a kind of 3D SoC. So from system innovation and heterogeneous integration point of view, with the scaling of the silicon node, still there's two ways to go. One is the SoC chip integration, another is SiP. So, and for the SoC and SiP actually is always competing. So you competed from the manufacturing point, maybe is silicon node, and the IP and IP use and basically for the design and engineering cost consider point of view, and for development cycle time, new product introduction cost, and also the hardware and software entire integration and performance trade-off and product market share strategy. You want to come out the product is version 1, 2, 3, somehow like that, and also, or you want to consider like from profit version like 12 directly. Another key point of view for our industry is actually is the supply chain variety and also the safety. You typically the fabless company don't want to at least has two sources of this supply to secure the delivery of the product to end customers. For example, current chip shortage for the entire industry, especially automotive, or people even thinking about maybe the entire advanced chip from TSMC will become a problem. From this progress of silicon node and the cost point of view, the industry actually start to respond from previous roadmap from ITRS convert to this HIR. And the key focus actually is HIRS is focused more on CMOS, Moore's law driving, and because the almost the end of the Moore's law, the HIR is focused more on system application driving. So for the actually heterogeneous integration point of view, high-end application mostly focused on is the FCPJ packaging. for FCBJ package, the left side is this 4 kinds of basic structure. If is only one SoC chip preview, this is either with stiffener ring or the stiffener ring past the spreader two piece of structure, or this forged dice lead for the better warpage control and also heat sink control. And then also this is a hell ties lead for different kinds warpage control. So with the 3D progress with multiple trees, so becomes a find out, for example, the CoWAS 2.5D with silicon interposer. So basically, this SoC chip becomes a 2-tree triplet or SoC plus HBM dash 2 or dash 2E. So then for larger FCPGA types triplet involved currently most advanced one is the first one is the CoWAS from TSMC or different company have the different name. Basically is this interposer use silicon TSV interposer, and the second one is the representative is the Intel's one EMIB. Then the third one is this the fan out on substrate, or RDL first RDL first die last one, or die first RDL last one, or this also the die last one also covers this fan out as fan out RDL as an interposer, and the third one is 2.1D. Basically, in our in our JSAC group, we call it UFOI of our XDFOI family. Basically, this is a fine RDL layer is embedded inside the PGA substrate. Or some other companies, 2.5D is building the fine RDL layer entirely on the RDL on the FCPGA substrate like Hitachi promoter. Then there's a sixth one is RDL on rigid substrate. Basically, this is something like Synco proposed. Basically, this organic substrate interposer with stick substrate. Then the die is a feature on it. Then also then attach on the typical FCPJ substrate. So basically, this the organic interposer also have the feature of 2-micron line space. So for 2.5D interposer case, previously the first generation actually is purely passive RDL interposer, but now because of this heterogeneous integration progress, started going to this active interposer. Basically, active interposer has both TSV as a basic feature, then also has this trench capacitor as a decoupling capacitor to improve the performance and like the voltage drop. Then is derived directly under the SoC or the other chip lips. So basically, the process flow is active interposer, just like the CoWAS approach, basically from the TSV and backend offline. Then the optional PIRDL on top of the with the optional inductor like IPD. And also the 2.5D assembly with die-to-wafer address when you can optional put in address the bar for stiffer control and warpage control or for molding. Then also the TSV backend exposed with the backend RDL and also the C4 bumping. Then this fan out or the 2.5D die package is friction mount on the substrate. Then finally attached with the landside capacitor or IPD, then placed with the solder board. So basically for our thinking as an OSAT, we basically consider the model is a foundry prepare the TSV wafers and like our JSAT does the rest. So here is another type of triplet application is CSP type fan out. or the chiplet application is first is diverse, like info, M series from a DCA or AC, then EW from our stat chiplet JSET and AC and Nani and Anchor. Then also the RDL last RDL on the carrier. These several other auto company are doing mainly is for high end or especially for Chile because the cost consideration and no good loss consideration. Somehow the RDL last on carrier is more preferred. And another is fan out on the subject. This is basically is diverse fan out for the smaller, relative smaller packaging because the yield consideration still valuable. Then the die loss are there on the carrier. This is also is for if we have multiple chiplet, consider no die loss. We also prefer the RDL loss on the carrier. Then another mention is this RDL hybrid substrate basically embed a fine RDL inside the substrate. It can be used in the CSP package as well. And this can, for example, use in the cordless substrate build up. This will provide higher performance because of the shorter interconnect connection. Here is another trend we can see from on the industry. Recently, this reverse engineering showed this Apple's M1 CPU application in the iPad or Mac. So basically, this is SoC die, and here is the memory. So then they use the half lead to control the thermal management and also the warpage. This is the structure from system class. You can see the difference from conventional this CPU. Then for challenge case, as this 5G and automotive progress, automotive also start to use this 2.5D and also SIP. But currently 2.5D and SIP's reliability performance still could not really meet the automotive industry requirement in terms of grade 1 and grade 0. For this one there's a long way to go. This is and we have to solve this reliability requirement, especially for the ADAs and also the automotive drive. Then in our JSF viewpoint view of the chip loss will be preferable to chip first the fan out for chip lead, mainly because the no good line loss. Manufacturing cycle time for high density chip first, the fan out is a showstopper because we have to go sequential process flow. And while for the truly RDL first case, we can proceed in parallel. So process yield concern on the multi-layer ultra high density RDL for the chip first, the OSAT is unable to the high the cost yield and in the no good die pricing. So that's another reason we have to use somehow prefer the RDL first chip last for Chile in our OSAT point of view. Then chip middle approach in fan-in POP may be another variable 3D option, and FC assembly on multi-layer ultra high density RDL with low dense backend RDL on the mold wafer. Somehow we call it is a fan out interposer. Optimized approach for the yield and cycle time and thickness would be permissible for this POP approach and also for other FC CSP's approach. And silicon interposer with TSV still will be required for high-end application with wide bus architecture like AIB of Intel promoter, and requiring sub-micron routing density. And for TSV release, RDL interposer preferred as alternative to silicon interposer, mainly because of the mid high-end routing density 2 micron feature and R2 for high density routing layer, mainly because the yield loss even with high density routing layer. So that's why we prefer limited effort high density routing layer. And silicon bridge will be difficult to implement for our OSAT in practice for more than a few die per package. Um, then JSI readiness for this application, we already developing this XD fan out 2.5D on the substrate. Basically, is RDL first with 2 tree or 3 tree or 4 tree. Then after the fan out 2.5D, we put the fan out package on top of the substrate with 14 to 20 layer of substrate. And then also the chip middle 3D POP, this application we have previously developed a year ago, but now we restarting this practice with chip middle 3D POP. This POP can be used for typical POP APU package, can also be used as an interposer, bridge interposer for high-end 2.5D chiplet packaging. Then also we are working with substrate supplier together for this XD fan out 2.5D hybrid substrate. Basically, we will build the RDL layer with less than 4 micron line space, and we deliver this RDL layer to the substrate supplier. Substrate supplier will build the additional layer on top of it, and before this collies or for the FCBGA application. Then the silicon interposer assembly case, basically we still mainly collaborate with foundry in advanced 5-pitch bonding. So this involve either the interposer on substrate first or die to wafer first, and then on substrate. Here it shows some our XD fan out 2.5D TS release process flow. Basically, for example, what we're working on is 65 by 65 pack size. That size is currently is 13 by 26, and silicon is like 7 nanometer, and with bond pitch of 330 micron with 14 layer of FCBJ substrate. BJ pitch is about 5 mm. So this package will be already codified. So basically, it's conventional this glass carrier with release layer. We build R3 layer of RDL, and after that we attach sheet, free sheet on the micropad, and after that we apply the molding. Then we do the debond and do the backwinding. Backwinding can be done either or also after the C4 bumping. Here we show is the first. Then we after debonding, we play the bond and singulate. Then this singulated package is attached to FCBGA substrate, applied with the underfill. Then after that, attached with the thermolit, then also attach this solder board and also lens side IPD capacitor, for example. So for this current XD fan out circulation case, currently we are prototyping mainly is a 4 metal layer. So then minimum VR size is 15, and minimum line space is 4 by 4, and maximum size is 14 by 14. R&D case we are doing currently is 4 micron still. Minimum VR size mostly is 15, but we are working on the 8 micron size as well. And line space, we are working with 2 micron line space. The mask size is 14 by 14, mainly constrained by the stepper. So basically, what we showing, we are using dielectric material is photosensitive polyimide material. RDL is made by the selective electroplating. The recommendation is there's no V1 opening for 2.1D application. So basically here shows the material some property basically at the different frequencies. So dissipation factor Q value is quite consistent across the frequency. That's the reason we choose the PI sensitive, photosensitive PI. And another application, we are basic technology for interconnection. We we use actually is the laser assisted bonding, which will be important for this, for example, college subject or other subject with higher warpage. And with the final package or the 3D package size becomes bigger, the total warpage also becomes bigger. So to minimize the warpage mismatch, we developed this. We also working on this laser assisted bonding process to reduce the cost. And also another consideration is for laser assisted bonding contribute less the stress on the ultralocate backend of the material. That's what the reason we're working on this laser assist bonding. And this laser assist bonding basically use this laser IR laser to heat up this silicon die, and which can be programmable with the different size, and then heat up the silicon to certain degrees of temperature, and also the PCB temperature is controlled like 70 to 80 degree. Then after reflow, you can be similar. You take a bond together with the micropad, then the warpage and also performance can be the yield can be much better control than typical MR or the TCB bonding. So here is our FCBGA roadmap. We can perform a single SOC FCBGA without lead, and also multiple die, and also we can manufacture this multi-package FCBGA, including the top side and the left side. We also have different kinds of even other components together for the automotive application. Then also multi-chip this FCBGA package. So for the lead type, we have a flat lead and also a ring type with this mold type exposed with field assist molding. Then also this SOC pass package type. We are working on this 2.5D TS release FCBGA with 2 die or 3 die or also 5 die. Then we are also working on different number of packages together with OC with this forge die lead. Then other types multi-packaging module FCBGA with HC. Then other market reference here shows you can see industry, for example, Samsung, they are working on the 3D FCBGA HD fan out multi-core module as well. So and also together with multi-die. Then from the Prisma, they can industry research report, it shows like AMD on chip network design to determine whether data center have deep chip to prevent the deadlock of with on the active interposer. So that part is also working on this. The Intel's Lakefield hybrid CPU use high bandwidth with this EMIB. Then the elite working on this active interposer. They do a very good explanation of this the active interposer's advantage and how to do it. Then also Z group working on the interposer with integrated passives, controlling the supporting power management and also this chip to chip interconnection. The integrated passive, if we're talking about chip capacitor in the interposer, is major advantage is can provide higher reliability over the 150 degree for automotive application. So here is typically the year research report mentioned what these different application for the 2.5D, 3Ds, or SIP application, including mainly is CPU, GPU, the FPGA, memory, and sensor, and also optical electronic performance. For example, photonic network application. Typically, people consider use silicon interposer with photonic circuit on top of it as an interposer, together with IC drive or porting type. Okay, that's what I have.
Thank you, Yao Jian. So I have collected some questions from your speech. The first one is, can you please comment on the thermal and mechanical challenges in the heterogeneous integration for high performance computing components applications? Because in there, the thermal and reliability requirements are way higher than the than the mobile applications.
Okay. For thermal application case, because this the hotspot inside the SoC, and and then design from a chip design point of view, when in the chip design, the thermal spot distribution will be important. Conventionally, most chip designer expect this our package can solve their problem, but nowadays they should also consider from the beginning of the chip design, consider to dispute this thermal spot uniform as much as possible. From assembly point of view, we prefer to have a thicker silicon die. That's the reason we did not background the silicon die. Mainly is for thicker silicon die to somehow redistribute the thermal spark to entire chip for the better thermal management. And then from the FCBGA packaging point of view, we are studying different kinds of TRM1 material, and industry even using this Indian TRM material with higher, I mean, snag cure or cure pressure to secure is or reduce is some resistance. And from mechanical point of view, reliability point of view, because multi-die, especially the die gap reduction. So this, if we apply the molding compound between, and also there's underfill material applied before molding. So the stress between die, especially for over two die, like 3 die or 4 dies, this this mechanical stress will be bigger. And during reliability test or even during assembly, if this underfill material or mold compound material is not select optimized properly, you will have this like die gap crack and even crack down to this RDL layer step, something like that. So this is the challenge we have to solve and also or somehow pay attention during development.
So do you see that we have actually existing, solutions to this, or and we are seeing investment needs in R&D to address all these?
At this moment, we see the solution there and can be implemented, but the window may not be really very comfortable to find out for all packages,
Mhm.
Yeah, have to fine tune individually for each kind of product.
Okay. So another question is about the EMI shielding for the for these SIPs. Do you have any comments on that?
EMI shielding currently still majority people still use this sparkling type, right? SUS copper, SUS,
Yeah.
and mainly is because its effectiveness. But with somehow the frequency go down to magnetic field, something like that, lower frequency, shielding effect is not so effective with this sparkling approach. Even we increase thickness or even consider like nickel iron, the impact is not really there. So from this point of view, this hybridize of this EMI may be necessary. For example, you have to apply first one layer of EMI for lower frequency, then you apply for typical sparkling this EMI shielding. Then though and another is EMI shielding case is because of the low cost consideration, because now capex for this sparkling indeed is high. people did try to develop this spread type of this EMI, but so far looks like adoption rate is not so high. So maybe because the reliability haven't really reached that level.
Okay. Uh, Another one is about the manufacturing testing, because you know that the SIP you cannot probe in, right? So
Yeah.
what is the technology or consideration on the manufacturing testing?
Manufacturing testing, actually, we depend more on this or partner with our end customer mostly, because different customer have different application. Some customer has even up to 10 or 9 tests for one FCBJ package, for example. Even for SIP package, for example, this IF type, we have to work closely with our end customers to develop this test program. uh, Not only the software, maybe some hardware, we have to co-design with our end customer and also the equipment supplier together.
Okay. Okay. Um, yeah. And the last question I would have is there any recent development on the advanced packaging technology in power management for large processors?
Yes, people try to incorporate this PMIC with relative large inductor, and also maybe also incorporate this IPN together with this large capacitor and large inductor, and for that, so different kinds development is ongoing. So even the size can be like thickness can be up to like 3 mm, even to 7, 10 mm, this kinds of thickness high.
Okay. Okay, thank you. So thank you, Yao Jian, for the questions. We for answering questions. We can handle more questions in the panel session. Now we have one little thing to announce. First, there is a poll about CASPA's activities that we need audiences to give us feedbacks on your opinions of our events. And another one, I would introduce our uh, BOV, Board of Volunteers, Richard Yan, who will introduce the coming events of CASPA. Okay, Richard.
All right, thank you, Ian. This is just the first set of the seminar. Thank you for what a great topic kick off the year. I'd like to everyone to stay tuned for our symposium group. We have 3 other major events that we planned. We like all our members, our sponsors to stay tuned, and I'll be also looking for very active participation to the event. I think the next event will be our spring symposium. Typically, we hold it in March. This timeline is still tentative because of the we are looking to settle the between the virtual and see if there's any other opportunities for the real event. We have a special interest group again seminar planned in April. This for Q2. And then summer symposium is planned in end of July. So please stay in tune. And you can look out in our events on our CASPA calendar site. Back to you, Ian.
Thank you, Richard. And also, so the audience, please participate in our polls. We have the polls there in at the bottom of the Zoom. And so now let's, at the same time, let's get into uh, the panel session, which means our question and answer, more expanded question and answer session. So I'm inviting Bill and Yao Jian to sit with us and answer the questions. So first, I have a couple of questions. The first question is to both of you, right? So what do you see are the important challenges for the HR? Well, I guess this question will be more for Bill because he's in HR.
Okay, let me see. Can you hear me?
Yes. Yeah.
Okay. I think the important challenges for HRR, um, there's quite a few.
Mhm.
And let me just start by talking about what does HRR do?
Yep.
HRR is a volunteer, and the roadmap is for everybody. And so what we need to do is to make the roadmap valuable. I'm very happy to see our speaker that you use some of the HR slides. That means that he has been reading it. So thank you very much for reading it. Now, what we want to do is to make sure that it becomes a tool for the industry. We have more than 150 volunteers in various parts of the chapters, and it would be very important for us to making sure that what we do is of value, value for the profession, value for the industry, and value for humanity. So that's number one. How do we, the biggest challenge for us is to make it be invaluable. So that is the challenge one. The challenge two, what we see in our roadmap is that if you read one chapter and you talk about item one, and you go to the second chapter, and it just says item one is also uh, discussed in the second chapter, but are they, do they reinforce and add value to each other? So the second thing we are working on very hard is to get the technical working group, the chapters, so that they together, they will be a good overlap. The overlap then would be looking at the same thing through different lens. In our industry, just like you mentioned, um, you asked earlier the question about passives, right?
Yep.
And so if there is the emerging materials chapter, I would want him to look at it and said, which what are the properties? What are the ones that we need? So these interactions add value to the chapter.
So that
And
means actually
that will make
expanding
it,
it, right?
yes.
Okay.
But the last one, I think, is probably is also on the personal level.
Okay.
Artificial intelligence, machine learning, data science. For myself, I need to go back to school and learn about data science, about data analytics, so that I could understand how to communicate with you and with Xiaojin, because we need to communicate with each other with data.
Mhm.
And how do we communicate just with data means that we need to be good at it. So I talk about on the personal level, I talk about it on the level of the people working in the roadmap, and I'd also talk about the readers of the roadmap. All these three are important for us looking into the future, because I believe that AI is going to drastically change the way that we do business.
Thank you. So the second question I have is also more to Bill, because I want to know, is there any example of the successful pre-competitive research that you mentioned in your talk?
Well, there is a in the May of this year, IEEE gave the Medal of Honor to Professor Chairman Hu
Yeah.
at Berkeley.
Yeah, he's our advisor, actually.
He's your advisor.
Yeah, he's CASPA advisor.
Yes. Now, back in 1995, people talk about the issues that they are seeing in the future of continuation of Moore's law. But at that time, the industry is doing very well.
Mhm. Yeah.
So, but there are people in DARPA who look out into the future and they send out a request for proposal. And Professor Hu, at that time in Berkeley, by fortuitous circumstances, he heard about it and he wanted to send in a proposal. But he needed to be in Tokyo. So on the flight from San Francisco to Tokyo, he sketched out his ideas on FinFET. And he got the funding from DARPA. 4 years later, technical papers, demonstration in the lab, so that the results are open for everybody to use. Intel picked it up first, tried it. Yes, they didn't need it, but they at that time yet. But it's years, 5 years later, we all enjoy the benefit of FinFET. So that's a pre-competitive research that we need, is that to look at it and say, we don't need it yet, but we know that when we need it, it's too late.
Yeah,
So
great. Mhm.
he also received the medal from Obama. He got a national medal for innovation. I think this is a classic example. Something we don't need yet, but you see the cloud in the you see the cloud in the horizon in the future, and so say let's get the work done so that we can enjoy the path into the future.
Well,
I think he
thanks.
extended Moore's law for 10 years.
Yeah, this is a very great example because we at Caspa we have really very dear experience with Dr. Chen Minghu. We had meeting with him, Zoom meeting a couple of months ago actually, a special advisor meeting that he gave us about what he's thinking about everything, and exactly as what you mentioned. So that's a great example of pre-competitive research. So the HR has 20 plus technical working groups, right? Are there any plans to add more?
Well, the answer is yes, we have discussions on what we need, and we have discussion and said, do we have the right leadership? So yes, we are looking at adding one or two, and we have a procedure to do that. But I can't really tell you right now because it will be discussed at our annual meeting on the 25th and 26th. Come to the annual meeting, and particularly on the Pacific time on the morning of the 26th, that will be on the table.
Okay, great. Great to know. The next question I have is who will benefit the most from the TSV-less chiplet integrations? It's either it's the legacy chipset vendors or the module vendors or the system vendors. So this question is for both. I mean,
for both. Okay, I would, since I answered the other questions first, I would give Yao-Jin the first answer.
Yeah, Yao-Jin, so.
Okay. I think TSV list, the first beneficent people, company should be the fabless company because they want to have multiple source supply. For TSV list, at least without additional requests from the support of foundry. So, and from supply chain point of view, is much easier. And also from the OSAT point of view, we prefer the TSV list because one reason is the supply and also this technical integration point of view. If we have TSV, if something happen between for different um, the different point of view from the foundry or from the outside is different, there will be some argument. So that then potentially be a problem. And also from end product point of view, the cycle time is not easy to control because of logistical and also this different production schedule.
Okay. And continue with another question to Yao Jian. So how is a chiplet-based SiP packaging project different from a legacy SoC chip? Will the collaboration begin much earlier, or will it involve much more technical alignment than before?
I would say this chicken and egg problem actually. Somehow the chili is preferred to be standard, but the end customer somehow they want to have different differentiates feature or different performance. So from that point of view, we prefer to have first alignment with end customers. Then because they may pick us on standard chili, they may pick up not standard chili, not customized chili. So basically chili, there should be two kinds of chili. One is standard modularized chili, another is custom-made chili, somehow like SOC or chili SOC. So we think it's necessary to align with customer first.
Okay.
Yeah.
Yeah. So and there's another question, mostly to Bill. Uh, just like the ITRS and any other technological advancements, there would be always pitfalls, which could eventually lead to improvements or total abandonment. So depends, right? Either improvement or abandonment. So what can you say are the pitfalls or disadvantages of HIR?
You're saying is that um, HR may lead people into the wrong direction. Is that what you're thinking of?
No,
right.
I mean from your own point of view, like it may have pitfalls, right? So what you see, it's something that you want to avoid, right? I guess.
Well, I think the important thing about HR to avoid is to avoid it as being identified as any specific commercial company, uh, commercial company's interest. So I work very hard to make sure that in the HRR, you could see in the HRR's PowerPoint, I do not list AAC. I list the societies. I list the sponsors. So it's very, very important that for HRI, it's identified as being a common interest. Is for the industry, for the profession, for the society in general, and not related to any company. At the same time, we need to making sure that HR is at the very front of the technology interest, so that people understand that what we are speaking about is at the frontier of the knowledge. And so these are the two things that we strive for, and we have been very lucky that we have good support, for example, from our advisory group, the advisory advisors that I mentioned to you. We have been very fortunate that when we are um, looking for questions, that looking for advice, usually it's given to us very, very generously. The other aspect is that between the technical working group members, we share confidential informations, and we have an understanding agreement that these confidential information do not go out is stay within the discussion working groups. So yes, there is different pitfalls, and we have. I was in ITRS for many years from the very beginning, so I learned about those pitfalls. And so when we do this one, we make sure that we stay within the straight path and not get to the pitfalls.
Okay, thank you. Next question is for both of you, I think. So the recent chip production cannot meet the high demand, and it caused the production lines such as the automobile companies to halt for weeks, right? Does the lag caused by packaging and assembly, and how packaging and assembly contributes to this issue, and what is the action to improve?
My own, so let me just give my response. Is that one aspect about heterogeneous integration is only use the most advanced chip where it is needed. And in that sense, it saves the foundry's capacity because it is the most advanced nodes capacity that is on the highest demand. So it has the advantage of time to market, the advantage of time to market, advantage of cost, but also advantage of its being able to balance the to give the foundry the opportunity to balance their capacity.
Okay. For automotive, from the it has one character is automotive qualification takes longer. So either from chip or from the assembly point of view. And current situation case, because the entire worldwide capacity, no matter wafer supply or the assembly supply is a problem. So it's hard to say what can we contribute, frankly. Yeah. Yeah.
Okay.
So basically, it really depends on the balance of industry planning, because currently this chip supply is mainly, frankly, is caused by this COVID-19.
Okay.
And yeah, but because the capacity was allocated to that relate like computing, CPU, or this. Yeah.
Yeah. So yeah, talking about COVID-19, right? So people actually a lot of people need to work from home, and the kids need to study from home, right? So there is a big demand actually for example, the terminals. So how does that I would say that how does this actually relate to like the packaging and assembly technology? So how can we achieve like terminals, for example, needs with a low price for education for all? This is kind of a more COVID-19 related question, but because of the specific uh, needs from the society.
Well, I just looked at the I just looked at this data from Prismark yesterday, and it talked about the increase in demand for desktops, for laptops and desktops, and it's it showed that so far it gives advantages to the supplier, but it doesn't seem to be overstripping their capabilities. So what I mean to say is that we all believe that this is temporary,
Okay.
and we all believe that today the suppliers, mostly they are in Asia, are able to meet the demand.
So I have the last question. So which stock would you invest in, Intel, AMD, or NVIDIA? That's the last question. For both of you.
I will be AMD.
Okay. So how about you, Bill?
No, I don't invest in stocks.
Oh, okay. Okay. So thank you very much. Thank you, Bill and Yao Jian, for your participating. And because you are our very valued sponsors, so this is also a way of our CASPA, to work with you to contribute to the society, to the professional society, semiconductors professional society community. Thank you very much, and we wish you a very successful business. And we'll see you soon. Thank you very much, and
Thank you.
everyone, thank you. Bye bye.
Thank you, everyone. Bye.
Thank you. Bye bye.
Okay, thank you, Ian. This is Xiaodong. I just sent you a file. I think a lot of people want to join WeChat group. I sent you one through the QR code through WeChat. Can you add it to your last slides so people can scan the code to join the WeChat group?
Okay. Okay. Just a second.
Sorry
Yeah.
about that.
Okay, no
Yeah,
problem.
the original one was expired.
Oh, okay. Okay, let me grab it.
Yeah.
In the
Just grab
WeChat.
to your last slides, and then so for people are still waiting for stay so late. Thank you so much for attending CASPA's the first SIG seminar. Thank you, Bill.
Well,
and
thank you
Yao Jian.
very much.
Yeah,
I
thank you. Appreciate
enjoyed it thoroughly. Thank
yeah,
you.
thank you. I know it's
Thank
kind
you,
of already late in East Coast.
Yeah,
Thank
yeah.
you so much for
Yeah. So Lin Ji, can you put it the code in the slide?
Yeah, sure. I'm doing that.
Yeah. So thank you. So Lin Ji is also the co-chair
No,
for the.
no. The one on the left expired. So I just sent you a WeChat one. Replace this one. Let me send to Linji as well.
It's the G3, right?
The G3, yeah, G3 was expired, I believe.
I just got one from the G3 is the one I got from you, right?
Okay, yeah, that one is good, but not this one. I think you are sharing the three picture. The one on the left is expired.
I just
So I
got,
want to, yeah, just showing the